May 12, 1940, 2:27 p.m., somewhere in the Ardennes, Captain Pierre Dubois, commander of a French tank company, stared in disbelief at the map. German tanks had just outflanked his position, but that was impossible. 2 hours ago, scouts reported the German column 15 kilometers to the north. Now they were in the south. How could they coordinate so quickly? Dubois dispatched a dispatch rider with new orders to his battalion. The rider needed 40 minutes to cover 8 kilometers. The orders arrived too late. German tanks had already broken through. What Dubois didn't know, every German tank commander was speaking directly to his comrades via radio. No dispatch riders, no delays, real-time communication on the battlefield. The Blitzkrieg wasn't just a tank war, it was a radio war. The radio communication system 10, developed in 1938 by AT&T equivalent, frequency range 27.2 to 33.3 MHz. Transmitting power 10 watts, range 8 to 12 kilometers over terrain. But the real revolution wasn't the technology, it was the philosophy. Germany equipped 90% of its tanks with radios, France 10%, Great Britain 15%, the Soviet Union 5%. The difference wasn't steel or cannons, the difference was information. How did the radio communication system 10 work? The technology was elegant in its precision. A super heterodyne receiver with 4 vacuum tubes, a transmitter with 2 tubes, frequency modulation for clearer transmission. A dynamotor converted the tank's 12-volt battery into 120 volts for the tubes. The device weighed 25 kilograms, but it changed warfare forever. German tank commanders communicated in real time. A platoon leader ordered 3 tanks simultaneously to outflank an enemy position. A company commander coordinated 12 tanks while on the move. A battalion commander spoke directly with artillery, air support, and infantry. The operational speed of German units was 2 to 3 times higher than Allied units. Not because of better engines, because of better communication. Let's compare the reality. French company, May 1940. Company commander sees enemy position. He writes the order on paper. Dispatch rider drives a motorcycle to the battalion commander. 20 minutes. Battalion commander approves. Dispatch rider drives back. 20 minutes. Company commander distributes orders to platoon leaders. 10 minutes. Total time from detection to action, 50 minutes. German company, same situation. Company commander sees enemy position. He speaks into the radio. All platoon leaders hear simultaneously. They begin to act immediately. Total time, 2 minutes. The difference, 48 minutes. On the battlefield. That's the difference between life and death. Between victory and defeat. The Soviet Union learned this lesson the hard way. June 22, 1941, Operation Barbarossa. German panzer divisions broke through Soviet lines with terrifying speed. Soviet commanders waited for orders from Moscow. German commanders made decisions in seconds, coordinated by radio. In the first 6 weeks, the Soviet army lost 20,000 tanks. Many were not destroyed in combat. They were overrun, outflanked, isolated. Because Soviet communication was too slow. General Dmitry Paulo, commander of the Western Front, recognized the problem immediately. In a report from June 28, 1941, he wrote, "The Germans communicate like an organism. Our units fight like isolated cells. They don't know what's happening to the left or right. They wait for orders that arrive too late or never arrive. The German advantage isn't armor or guns, it's communication." Paulo was shot. Stalin's response to disasters was always the same: shoot the messenger. But the problem remained. The Red Army had radios, but too few. Only regimental commanders had access. Companies and battalions fought blind. German units operated like a network. Soviet units operated like isolated islands. The technical difference was dramatic. A German tank platoon, 1941. 5 tanks. Every tank had a radio communication system 5 receiver. The platoon leader's tank had a radio communication system 10 transceiver. The platoon leader could speak to all tanks. The tanks could hear the platoon leader. Simple, effective, revolutionary. A Soviet tank platoon, 1941. 5 tanks. Maybe the platoon leader had a radio. Maybe, if it worked, if batteries were available. The other 4 tanks had nothing. Communication occurred through flags, through light signals, through couriers running between tanks. In the chaos of battle, that was impossible. Kursk, July 1943, the largest tank battle in history. The Soviet Union had learned, after 2 years of desperate fighting, the Red Army had improved its communication. But still, German coordination was superior. First Lieutenant Hans Weber, commander of a Tiger platoon, described the reality. We talked constantly. Every observation, every movement was shared immediately. If one tank saw a T-34, all 5 tanks knew instantly. We hunted like a pack of wolves. The Soviets fought like individual bears. Soviet reports confirmed Weber's observation. Colonel Iwan Kozlow, T-34 battalion commander, wrote in September 1943, "German tanks move like a unit. Our tanks fight individually. If I want to issue orders, I have to get out of my tank and run to each platoon leader. The Germans sit in their tanks and talk. The difference is life and death." The Soviet solution: steal German radios, analyze, copy, reverse engineer on an industrial scale. Every captured radio communication system 10 was sent to Moscow. Engineers disassembled them, measured every resistor, every capacitor, every coil, tried to understand how German precision worked. But it wasn't easy. German radios were based on vacuum tube technology from AT&T equivalent and Lorenz. The tubes were precisely manufactured, with tolerances of a few micrometers. Soviet factories couldn't achieve such precision. Early Soviet copies functioned poorly or not at all. The frequencies drifted, the range was limited, the reliability was catastrophic. A Soviet engineer, Sergei Ivanov, described the frustration in a 1944 declassified report. "We have the schematics. We understand the theory. But German manufacturing is unreachable. Every tube is perfect. Every capacitor is exact. Our components vary. One radio works. The next one doesn't. We produce gambling, not technology." Indeed, the turning point came in 1945. Germany surrendered. The Soviet Union launched Operation Paperclip, a systematic, planned abduction of German scientists and engineers. On the night of the 21st, October 22, 1946, the NKVD arrested over 2,200 German specialists, rocket scientists, aircraft engineers, chemists, and radio technicians. Telefunken engineers were taken directly to Soviet research institutes. Their families were held as hostages. The message was crystal clear: work for us, or your families suffer. Dr. Heinrich Müller, a leading engineer at Telefunken, later described the experience. "We were put on a train. We headed east. We didn't know where. After 3 days, we arrived at a secret research complex near Moscow. They gave us paper, pencils, components. They said, 'Build your radios, just like in Germany.'" The Soviet copy of the Fuji-10 was designated the R-105. Development began in 1946. Production started in 1952. 6 years. It took the Soviet Union 6 years, with stolen blueprints and abducted engineers, to copy a German radio that had been developed in 1938. But even then, the R-105 was inferior. Range 5 to 8 kilometers. The Fuji-10 achieved 8 to 12 kilometers. Reliability 70%. The Fuji-10 had 95% reliability. Weight 32 kilograms. The Fuji-10 weighed 25 kilograms. The Soviet Union could copy German technology, but achieving German precision was impossible. The irony: by 1952, the R-105 was already obsolete. Modern radios use transistors instead of tubes, frequency modulation instead of amplitude modulation. The Soviet Union had spent 6 years copying technology from 1938. The world had moved on, but the journey there was fascinating. The Soviet engineers struggled with every detail. The biggest problem was tube manufacturing. German Telefunken tubes had a lifespan of 2,000 hours. Early Soviet copies lasted 300 hours. The difference was in the vacuum quality. German factories achieved vacuums of 10 to the power of -7 torr. Soviet pumps only managed 10 to the power of -5 torr, 2 orders of magnitude difference. That sounds small, but in tube technology, it's critical. Dr. Müller, the abducted Telefunken engineer, explained to the Soviet technicians, "A tube is like a tiny world. Every atom counts. If there are too many gas atoms in the vacuum, electrons collide with them. The tube gets hot. It loses efficiency. It dies early." German vacuum pumps were masterpieces of precision. Soviet pumps were adequate for many purposes, but not for high-frequency tubes. The Soviets solved the problem through brutality. Instead of producing one perfect tube, they produced 10. They tested them all. They kept the 2 best. The other 8 were scrapped, inefficient, wasteful, but it worked. Somehow, despite all that, the Soviet Union produced 32,000 R-105 units between 1952 and 1960. They equipped T-54 and T-55 tanks with them. The Korean War, the Vietnam War, the Six-Day War. Soviet tanks communicated with technology based on German designs. The Soviet soldiers didn't know it, but every time they pressed the radio button, they were using German engineering. A fascinating example of technological appropriation, the dynamotor. The Fuji-10 needed 120 volts for the tubes, but tanks only had 12-volt batteries. The solution was a dynamotor, a combined electric motor and generator. The motor ran on 12 volts. The generator produced 120 volts. Elegant, efficient, but hard to build. The German dynamotor in the Fuji-10 was a precision instrument, ball-bearing shaft, carefully wound coils, commutators with precisely dimensioned segments, efficiency 78%. That is, 78% of the electrical input power was converted into usable output power. The Soviet dynamotor in the R-105 had an efficiency of 62%, a 16 percentage point difference. That doesn't sound like much, but it meant the R-105 needed larger batteries, or the batteries lasted shorter, or both. In a tank, where every kilogram counts, that was a real problem. Why the difference? German ball-bearing manufacturing was superior. German coil winding was more precise. German quality control was stricter. Small differences in each step accumulated into large differences in the final product. The technical influence continued. The R-113, developed in 1958, was based on R-105 principles. The R-123, the standard tank radio of the Cold War, used circuits directly derived from the Fuji-10. The R-168, used in modern T-90 tanks, has a technological lineage that goes back to Telefunken in 1938. But it wasn't just the Soviet Union. The Americans also analyzed German radios. Operation Paperclip brought German engineers to the US. The British BIOS, British Intelligence Objectives Subcommittee, confiscated tons of Telefunken documents. French troops dismantled German factories and transported the equipment to France. A specific example of American appropriation. In July 1945, the U.S. Signal Corps seized the entire Telefunken research facility in Berlin-Tempelhof, 127 tons of documents, 43 prototypes, 18 senior engineers. The commander's report, Colonel William Preston, is revealing. These Germans are 10 years ahead of us in high-frequency technology. Their circuits are more elegant, their components are more reliable, their manufacturing methods are more efficient. We must learn everything they know. The U.S. Army established the Radio Research Laboratory at MIT. German documents were translated, German circuits were analyzed, German methods were adopted. The SCR-610, the standard American tank radio from 1950, used circuit designs directly from Fugi-10 blueprints. The Americans didn't admit it, but engineers who compared the schematics saw the truth. The British were even more direct. They abducted Dr. Wilhelm Runge, chief engineer at Telefunken. They took him to Malvern, to the telecommunications research establishment. They sat him in front of a blank sheet of paper. They said, "Draw everything you know." Runge drew. For 2 years. The result, the British WS-19 radio, which was used until the 1960s. It was essentially a Fugi-10 with British components, modern tactical military communication, the AN/PRC-117F of the USA, the Thales PR-4G of France, the R-168 of Russia, all are based on concepts that German engineers developed between 1935 and 1940, frequency hopping. Telefunken experimented with it in 1943, encrypted communication. The Fugi-10Z had rudimentary encryption, network-centric warfare. The Wehrmacht practiced it from 1939 onwards. Here's a particularly fascinating detail. The modern American sync Gauss radio, used from 1988 to today, utilizes frequency hopping with a whopping 2,320 frequencies per second. The idea, Telefunken engineers developed it in 1943 for the Fugi-25A IFF system. The implementation is more modern, sure, but the concept is identical. Constantly change the frequency so the enemy can't jam you or eavesdrop. SynGAS costs around $8,000 per unit. The US Army has purchased over 600,000 of them. That's almost $5 billion for technology based on German concepts from 1943. This isn't criticism, mind you. This is recognition. Good ideas are universal, and German engineers had very good ideas. The story of the Fugi-10 is the story of a technological revolution that forever changed warfare. Before the Fugi-10, armies communicated like it was the 19th century. Messengers, flags, light signals. After the Fugi-10, real-time coordination was the standard. Every modern army, every modern military, every modern warfighting doctrine is based on principles Germany developed between 1935 and 1940. The technical details of the Fugi-10 are fascinating. The transmitter used an RV-12P2000 output tube, which delivered up to 10 watts of output power. Modulation was amplitude modulation, simple but effective. The receiver was a super heterodyne design with an intermediate frequency of 3 MHz. The antenna was a 2-meter rod mounted on the tank turret. German engineers also solved the problem of electrical interference. Tank engines generate massive electromagnetic interference, spark plugs, alternators, electric motors. They all produce noise. The Fugi-10 had elaborate filtering, capacitors, chokes, shielded cables. The result, clear communication, even while driving, even while firing. The Soviet Union struggled with this problem for years. Early R-105 units had terrible interference issues. If the engine was running, the radio was almost useless. German engineers had thought of every detail. Soviet engineers had to painstakingly reconstruct every detail. Another German innovation was ease of use. The Fuji-10 had large, clear knobs and switches. A tank commander wearing gloves could operate it. Frequency selection was with numbered channels, not with precise frequencies. Channel 1, Channel 2, Channel 3. Simple, foolproof, brilliant. Soviet radios were more complicated, fine adjustments, small knobs, complex procedures. In the chaos of battle, this was impractical. German ergonomics were a weapon. Soviet complexity was a weakness. The psychological effect of German radio communication was enormous. Allied soldiers regularly reported the feeling that German units always knew where they were. German tanks seemed to coordinate as if they were controlled by a single intelligence. This wasn't a mystery, this was the Fuji-10. An American officer, Captain Mike Johnson, described a battle in Normandy in August 1944. We engaged a lone German tank. Within minutes, 4 more German tanks showed up. They knew exactly where we were. They coordinated their movements perfectly. We didn't stand a chance. Later, we found out every German tank had a radio. They were talking to each other. We had 1 radio per company. We were fighting practically mute. German radio doctrine was also innovative. German tank commanders were trained to communicate constantly. Observations, movements, intentions, everything was shared. The concept was, more information is always better than less information. Allied doctrine was restrictive, maintain radio silence, except when absolutely necessary. The fear was that the enemy could eavesdrop on the communication. A concrete example of these doctrinal differences, Araucourt, September 1944. The U.S. 4th Armored Division fought against the German 5th Panzer Army. American tanks had technologically better radios. The SCR-508 with 20 watts of transmit power and frequency modulation, but American commanders rarely used them. The doctrine was radio silence until enemy contact. German tanks had the older Fuji-10, but they communicated constantly. First Lieutenant Klaus Richter, commander of a Panther platoon, described his typical radio traffic. I spoke every minute, position of enemy tanks, terrain features, my intentions. The intentions of my comrades, we built a shared picture of the battle. The Americans had better radios. We had better communication. The result at Araucourt. German tanks, outnumbered 3-1, destroyed more American tanks than they lost. Not because of better technology, because of better use of the technology. The US Army learned this lesson, but it took years. The FM 17-12 Tank Doctrine Manual from 1950 first emphasized continuous radio communication. The idea came directly from analyzed German tactics. American officers who had observed German tank units in combat wrote the new manuals. German engineers partially solved this problem with the Fuji-10Z, a version with simple voice encryption. The encryption wasn't particularly strong, but sufficient for tactical communication. Allies could intercept German radio, but decrypting it took too long. By the time the information was useful, the tactical situation had changed. The Fuji-10Z used a rotating codebook system. Every day the code changed. The encryption was a simple frequency transposition with variable keys, not unbreakable, but time-consuming to decrypt. In a fast-moving tank battle, time was everything. Even 10 minutes of delay made the information worthless. British codebreakers at Bletchley Park could decrypt Fuji-10Z traffic, but it took an average of 4 hours. By that time, the German tanks were 40 kilometers away. The information was historically interesting, tactically useless. Another technical aspect that is often overlooked, antenna technology. The Fu-G10 used a 2-meter whip antenna, simple but brilliantly designed. The antenna was spring-mounted. It could withstand vibrations, shocks, even direct hits from shell fragments. It could be adjusted to any length between 1.4 and 2 meters to optimize the resonant frequency. Soviet antennas on the R-105 broke constantly. The mount was rigid. Vibrations from heavy tanks were transmitted directly to the antenna. After 100 kilometers of driving, the antenna was often broken or bent. German antennas lasted thousands of kilometers. Why? Because German engineers thought of every detail. Soviet engineers copied the design, but they didn't understand the principles behind it. The production of the Radio Communication System 10 was an industrial masterpiece. AT&T produced roughly 250,000 units between 1938 and 1945. That's almost 100 units per day for 7 years. Despite Allied bombings, despite resource shortages, despite chaos, German quality control remained strict. Every radio was tested, defective units were repaired or scrapped. The reliability rate stayed around 95%. The Soviet Union tried to achieve this level of production quality and failed. R-105 production had a 30% failure rate. A third of the units produced didn't function correctly, or at all. Soviet factories lacked the precision, the quality control, the culture of perfection. German engineers learned precision over years of training. Soviet workers learned production in weeks. One particularly fascinating detail: German radios received regular maintenance every week, cleaning every month, inspection every quarter, calibration. There were dedicated radio workshops in every division. Trained technicians kept the equipment in perfect condition. The German military treated radios like precision instruments because they were precision instruments. Soviet tank crews treated radios like ordinary equipment. No maintenance, no care. If it broke, it was thrown away. The mentality was, we have millions. Losses are acceptable. The German mentality was, we have few. Each one must function perfectly. 2 philosophies, 2 cultures, 2 results. The modern relevance of this story is astonishing. Every modern military doctrine emphasizes communication. Network-centric warfare, the American concept, is essentially Blitzkrieg with satellites. The idea: give every unit real-time information, coordinate on all levels simultaneously, move faster than the enemy can react. That's exactly what Germany did in 1940, only instead of GPS and digital data links, they had Radio Communication System 10 and voice communication. The principle is identical. Information is the ultimate weapon. Whoever communicates faster wins. These technologies aren't just history. They're in every modern military radio, in every tactical communication system, in every doctrine about real-time coordination. German engineers of the 1930s laid the foundation of modern warfare, from Blitzkrieg to GPS-coordinated airstrikes, from radio-equipped tanks to drone-controlled swarms. The technical lineage is direct and clear. If you appreciate these technical truths, support with YouTube's Super Thanks. Every Super Thanks allows me to dig deeper into archives, to digitize rare technical documents, to interview surviving engineers. Help me preserve this technical history, because this story isn't just about the past, it explains our present. Technical analysis shows the Radio Communication System 10 wasn't just a radio, it was a paradigm shift. Before 1940, armies were hierarchical and slow. After 1940, modern armies were networked and fast. The Radio Communication System 10 was the bridge between 2 eras, And the Soviet Union, desperate after defeats, stole that bridge, copied it, and tried to catch up technologically. They partially succeeded. The R-105 worked, but it was never as good as the original. German precision, German quality, German engineering that couldn't simply be copied. It had to be developed over generations, cultivated, perfected. What German technology has surprised you the most? Many engineers in the comments have pointed out incredible connections, grandfathers who worked at AT&T, blueprints in company archives, modern radios with German circuits. Share your technical discoveries. Every comment is a piece of the puzzle of technical history. The story doesn't end in 1945. It continues. Every technical innovation builds on previous ones. The Radio Communication System 10 led to the R-105. The R-105 led to the R-113. The R-113 led to the R-123, and so on, to modern digital systems. But the basic idea, real-time battlefield communication, was perfected between 1935 and 1940 by German engineers. In the secret archives, there are documents recently declassified that show the Soviet Union knew their communication was inferior. Reports from 1941, 1942, 1943 all say the same thing. German coordination is superior. Our units fight in isolation. We need German technology, and after 1945, they got it through theft, through abduction, through systematic looting of German science, Operation Paperclip. But here's the final, uncomfortable truth. Even with stolen technology, even with abducted engineers, even with copied blueprints, the Soviet Union took years to achieve what Germany had developed in months. Why? Because technology isn't just blueprints. Technology is culture, training, precision, quality. You can steal plans, but you can't steal excellence. German AT&T engineers trained for years. They didn't just understand how radios worked. They understood why they worked. They could improvise, improve, innovate. Soviet technicians copied, but copying isn't understanding, and without understanding, there's no true innovation. The Radio Communication System 10 was a product of German engineering culture, precision for its own sake. Quality as a fundamental principle, innovation as the standard. That culture can't be copied. You have to live it. And that's the real reason why German technology was so hard to replicate. One last technical detail illustrates this philosophy perfectly. The instruction manual for the Radio Communication System 10 was 47 pages long. The Soviet manual for the R-105 was 12 pages long. German engineers explained every detail: how to use the device, how to maintain it, how to diagnose common problems, how to perform simple repairs. The manual was a masterpiece of technical communication. The Soviet manual essentially said, turn it on, set the frequency, speak. If it doesn't work, take it to the workshop. No diagnosis, no maintenance, no repair. These differences in documentation reflect differences in philosophy. German engineers wanted users to understand the technology. Soviet engineers only wanted users to use it. The lesson is universal and timeless. Technical superiority doesn't come from resources or numbers. It comes from culture, from training, from a commitment to excellence. Germany had fewer tanks than the Soviet Union, but every German tank communicated. Quality ultimately trumped quantity for a time, until quantity became so overwhelming that even superior quality wasn't enough to win the day. But that is another story entirely, a story for another time. A story best told with a cold beer and a long evening. The kind of story that makes you appreciate the freedoms that so many fought for. It's a story about the limits of even the best technology, when faced with the sheer, relentless, overwhelming tide of manpower and resources, it is a story that serves as a stark reminder that even the most advanced machines of war are ultimately tools in the hands of men, and that the human element, the will to fight, the ability to adapt, and the courage to persevere are qualities that no amount of technology can ever truly replace. A story that echoes the brutal truth that in the end, wars are won or lost by the soldiers in the trenches and the tankers in their machines